So this can be proved mathematically, and I'm highly incompetent in mathematics, so I'm not going into that. So for any volume that you want, if you want to decrease its surface area, you need a sphere. And why are the raindrops spherical in shape? Like in general, bubbles, like soap bubbles. Why are they not cylindrical? Conical, cubes, like why they're always a sphere? Really interesting. Like if you just think about it.
Would it be because it's less surface area, so it's like less friction when it comes down or something like that? Because it's like less area, or
more area means more space for reaction. Like you see this was one of the areas in which reaction was happening. So when you have the exposed areas, whenever you have an exposed area, that means you have more opportunities for interaction with the outside world. And that is why in here, so that is why anything like in nature is whenever it is weathering it out, why is it choosing to become a sphere? That's what it is doing. It is chipping away all the surface areas and it's trying to make it sphere so that it has the least amount of energy. So sphere will always have the least amount of surface area and therefore the least amount of energy associated with it. So that's the most stable form, a sphere. And that is why you will see this thing in many places in natural world, many places. So everything tends to become a sphere to lower its energy, become more stable. Okay? This thing is becoming a sphere. So when you are becoming a sphere, so anything that looks like kind of like rounded, it is becoming like a sphere. You can also think of this as more branching, less surface area. So there is more branching, the branches coming out of the main thing, more branches coming out. When you have more branching, you're making the area lesser and lesser. And the van der Waals is basically an interaction. And the more exposed surface that you have more interaction. So in here, the van der Waals is the least because of branching. Understand this, the branching is decreasing its area. The less area is decreasing the van der Waals interaction. And that is why its boiling point will be what?
lower?
But now let's move to this thing, or in here, group 16. So when you have more molecular weight, you are becoming more and more solid. Like you're increasing the molecular weight, you're going more towards a solid regime, right? Because you see, in non-metals, in the metals, group 1A, so you have lithium, sodium, potassium, rubidium, cesium, francium. By the time you have reached cesium, it's solid. Sodium was cheese-like almost in texture. But when you reach sodium, because of the increasing weight, atomic weight, it has turned to like solid. So as you're moving down the periodic, as you're moving down the group, you're becoming more and more solid oriented. Again, group 17. Very good example. F2 and Cl2, what's the state in nature? Solid, liquid, or gas?
Yes.
Bromine can exist in liquid state. So bromine is a liquid. Iodine is a solid. Iodine is a solid. So that the tincture iodine or the iodine that you get in the shops, that's not just iodine, that's an iodine in a solution. But iodine is iodized salt, so it's solid. So you see, when you moved to a higher and higher molecular weight, you are getting more and more towards that solid. But in here, this is liquid, but H2S is a gas. Hydrogen sulfide is a gas, and hydrogen oxide, which is water, is liquid. Why is that? This should have been the reverse. This should not. How is this? This should also be gas. Why do you think H2O is liquid? It should be gas. Because a higher molecular weight thing still exists as a gas. There should be something that is making it more stable. It's decreasing its energy. So now when you're comparing, let's compare gaseous H2O, which is vapor, liquid H2O, which is liquid water, and ice. Which of them has the least energy? Ice has the least energy. So generally solids have lesser energy than liquids. Liquids have lesser energy than gas. And why is that? How do you know? Can you give me a physical interpretation of how do you think, or why do you think solids, exactly, the movement. If they're not moving that they're moving, they're not moving that much. The liquids and the gases are moving a lot. So these two things can flow, and these two things are called fluids. Things that can flow, fluids, so liquid and gas. And gas is like the highest energetic. So in here, this should have been a gas. But there is something that is decreasing the energy of H2O gas, and because of that decrease in energy, it is shifting from gas to a liquid. There's something decreasing the energy. So we saw bonds can decrease energy, and then we are moving into some interactions that can decrease energy.
Would it be temperature?
It is the hydrogen bonding.
It is the hydrogen bonding, but what about temperature?
Oh, I was just thinking about like.
It's the same temperature. So at room temperature, if you're comparing H2O and H2S, both at room temperature, one is a liquid, one is a gas. But logic suggests that if this is a gas, this should also be gas. But somehow this is not a gas, because there is an additional force of attraction that is occurring between the H2O molecule. So there is a delta minus here, so this is getting a delta plus. There is another O coming in, maybe something like this. That is happening here. There is a particular way you can draw this. I'm not going to attempt to draw it today because I'll definitely do it wrong. So I'll go back, look at a diagram and come back. But I know this, that each H2O bonds with, or hydrogen bonds with 4 other H2Os. So there's a huge amount of interaction, and that too, the best or the highest form of interaction, hydrogen bonding, that occurs. And because of this huge amount of hydrogen bonding that is happening in H2O, we get strange properties of H2O. And that is why this is liquid, by the way. Water is a strange compound. Ice floats. Why is a solid form floating in its liquid form? Why?
It's less dense.
Huh?
It's less dense.
It is less dense. Obviously it is less dense. But the question is, why is it less dense?
Would it be because the surface area or whatever, like not the surface area, but like why some animals can float on water?
Exactly, and you're going in the right direction. Why? Why does a ship float on water?
Buoyancy.
More buoyant.
Buoyant. Why is it buoyant?
There's more vacancy.
The surface area.
So what do you think, just imagine, is happening when H2O is getting frozen?
Well, it doesn't it lock and expand? Isn't the weight, the density of ice like 90% that of liquid water? So putting in that 10% difference. That's why you see 10% of an iceberg, 90% of it's underwater.
Yeah, that's exactly. But the thing is, like, when you have that ice, so basically you're saying that ice is less dense than water. So if the density of water is 1,
It's 0.9.
it's 0.9, the units. Why? Because none of the other solids are doing it, or normally that doesn't happen.
It has something to do with like
Just imagine in your
the
heads,
bonds.
for just a moment, just imagine that you have liquid and then you're trying to freeze it. Okay? So that liquid is already in interaction with 4 other four other H2Os. It's not just a random thing it is associated with 4 others. And it is now freezing, or in the process of freezing or decreasing energy, what is happening is it's vibrating less and less. That's what is happening, right? It's vibrating less and less, coming together, coming closer. Because from liquid, if you want to go to a solid, that's what you're essentially doing, you're coming closer. But since you're also interacting, so now I'm H2O in liquid, and I'm interacting with 4 others, and we're in the liquid state, and now the temperature is decreasing. So my energy or my vibration is decreasing, but the interactions are still on with the other H2Os, right? So I'm like I'm moving less, but I'm still in touch or in contact, interacting with the other 4s. So while I am freezing, I am like coming closer to all these 4, and when people are coming together with this really strange interaction, that interaction, which is hydrogen bonding. So because of that hydrogen bonding, that freezing is not a usual freezing. It's a freezing with that interaction. So there is a very specific way the H2O molecules get locked up. They are not able to get as close to them, as close to the others as possible, because of that strange interaction with the other 4s. And because of that, there is a space between the H2Os. Because of that space, its density becomes lower. It's a consequence of this hydrogen bonding. Very important. If this didn't happen, then when you freeze a lake, only the top, it freezes. The rest is still liquid water. Important for fish life and all marine life, because you need liquid water.
Does methane do the same on Titan? Does it freeze at the top and is it liquid
I don't
below?
think so, but I don't know. But I do not believe that the same thing will happen, because you can have liquid methane, and then if you freeze it, there is no such interaction between them. So if it freezes, I think it will freeze
all the way through.
Yeah.
When you have frozen, you have ice and water, are the bonds on the outside, other oxygens trying to
Bonds on the outside? What outside? On the layer?
like the surface area of the ice, are those because they're
It's the same
more-
logic.
so
It's
they
more
try-
exposed. So they're hanging bonds. That's not much interaction. Those hanging bonds, so I needed 4 breads to satisfy my appetite. I'm only getting 2. I'm not getting 2 breads.
Okay.
So my appetite, so I'm more reactive.
Okay.
I'm not satisfied.
Okay.
So my bonds are not satisfied.
Which is why which is why ice starts to melt because those bonds are trying to leave, or they just melt because of the temperature.
Ice will melt because of the temperature.
Okay.
Right. The melting is the temperature. Because if you take ice at say negative 50 degrees Celsius, so it's not melting, but it's still more reactive on the outside.
Okay.
Because its bonds are, and that's true for anything.
Okay.
If you have a mineral, it's true for that. So reaction will always start from that part, which is the most reactive, and the most reactive parts are those in which there are less bonds.
Okay. And can you put all the bondings from like the least, like this, like not the strongest to the strongest? between
Oh yeah,
all of
okay.
them?
Let's do that next class.
Okay.
Yeah, okay. I'll have to go back because I don't remember.
Okay.
I have to go and like, I know like out of all these, like all the van der Waals, iron, what
Okay.
these missiles, okay, I'll do that.
Okay.
And since you have, I'll also give you a mathematical, like how, because some of these, so the bonds are dependent on r squared, negative of r squared, but some of these are dependent on -3s, -5s, -6. So that will give us the exact mathematical logic behind their in this interaction.
Okay.
I'll give, I should
I'll
have
shoot you an email, we'll schedule something.